In the name of Allah, the most compassionate and the most merciful. Hello everyone, welcome back to the channel. I am Salah Qashqai. Today we are diving into the interesting topics for mechanical and structural engineering. This video focuses on thermal analysis of concrete and steel frame structures, and we are going to model it with OpenSees as a two-dimensional modeling. Thermal analysis is an essential when considering temperature effects on materials, structures, and especially environments with significant temperature variation. So we are going to develop the OpenSees code to define the geometry, material, loads, and temperature profiles, and run it and simulate this kind of analysis. You see guys, in here in this picture we have two kinds of structures: concrete frame structures and steel frame structures as a two-dimensional modeling. So first of all, let's see the concrete frame structures. You see, in these concrete frame structures we have 4 bays, 3 stories, and 20 nodes, 27 elements, and 60 degrees of freedoms. So both of these concrete and steel frame structures subject to the thermal and distributed loads. So thermal gradients simulate the fire exposure, increasing beam's temperature until 300 degrees of Celsius to the first floor beams. So we are going to apply the uniform distributed load for all beams of these structures, and just we are going to apply the thermal loads just in the beams in first floor. So these thermal loads applied at the bottom side of the beam section until top of this beam section. So for concrete we are going to define the concrete two thermal materials: linear tension softening for definitions of the concrete material properties for this concrete section, and also steel thermal materials for defining the materials of the steel rebar properties. So, and we have two kinds of concrete sections. For beams we use this section, and also for columns we use this section. So after running this thermal analysis, you see the form shape of these structures is like this. So I defined the form scale as a 10 times for better plotting the deform shape. You see the deform shape, and you see these nodes because the thermal loads applied it just for the beams of the floor of story 1, and you see the form shape is like this. And let's see the other data outputted, such as base axial reactions and displacement of node 6. You see, I mean this displacement. So we're going to output the lateral x directions of these nodes to plotting the base axial reactions and displacement both in x and y directions. You see, it is the x direction and base reactions in base reactions of all nodes. And let's see other outputted data: base moment and rotation of node 6. So it means that we're going to output the base moments of these nodes and then outputting the rotation of this node. And let's see temperature and middle span node of this 18 node. So it means that we're going to output the lateral as x and y directions of this node as a displacement by the temperature effect as a thermal loads. And you see in x and also y directions we're going to plot it. See guys, thermal and displacement of node 18, it has this shape. And also we're going to output the strain and stress relations of bottom and top fibers of concrete of beams, I mean these positions. So the bottom side and also top side of this beam section, we're going to output the strain and stress relations. So by the process of this thermal analysis, we're going to see the different results such as displacement and base reactions and also strain and stress relations like this, you see guys. So let's see the steel frame structures. So in steel frame structures, all the structures properties is the same as a number of bays, number of stories, and also we're going to apply the uniform distributed loads for all beams, and we're going just to apply the thermal loads just for the beams in a story of 1. And we're going to define the different kinds of sections. For example, in this Python code, I defined 5 types of steel sections. You can change it with your own parameters. For example, I sections, box sections, pipe sections, rectangular sections, and also double I sections. So in this example, we are going to just define the beam sections as this section and also column section as this section, and run it this thermal analysis, and you see. So we're going to apply this temperature from bottom until top of this I section for beam of story 1, and then seeing the result. You see the resulting base axial reactions of these nodes and also shears and moments also, and displacement of this node is going to be shown in here. And you see displacement of node 6 and base shear. It has this shape. So node 6 and base reactions of base shear of this properties, and also node 6 rotations and base moments. So we're going to also output these nodes rotations and base moments of all base nodes, and also temperature and middle node 18 displacement as a x directions. So we're going to see the effect of temperature effect for displacement of x and y direction of these nodes. So you see the x directions and also y directions effect is going to be shown in here, and also strain and stress relations for elements 6 top and bottom fibers of these I sections. So this fiber and also these fibers of element 6 as this element, we're going to output the strain and stress relations during this thermal load analysis. So let's see the Python codes. First of all, concrete and also steel frame structures. You see guys, in here we develop the Python code, and using the OpenSees we're going to use these libraries, and also defining the different concrete sections for beams and also columns, which I told you. Number of stories, number of bays, story height and bay weight. So it is going to be defined, and you can change it with your own data. And also steel rebar properties for rebar as a steel one thermal, we're going to define it, and also concrete properties, we're going to define it as a concrete 2 thermal, and also we're going to define the thermal and distributed load in here. So the maximum thermal is 600 degrees Celsius and distributed load is minus 0.003 as a kilonewton per millimeters. And also we're going to define the analysis properties, maximum iterations and tolerance, and we're going to apply define the number of incremental steps for this force control analysis. And also in here we're going to define the nodes and boundary conditions, material properties for concrete and steel frame structures, and let's see, we're going to define the rectangular sections properties such as width and height, and also cover steel rebar diameters, and also number of fibers in the concrete sections properties. And also we're going to define the concrete section and also column sections properties. So we have two kinds of sections for beams and columns. So let's see this function which I developed by myself. So in concrete fiber thermal sections, you can see that I defined some functions for definition of these thermal fiber sections. You see in here I defined this section as a beam for definitions of the beams properties, and also we can plot it by definition of true or false. And you can change it with your own parameters. And also for the column, I define these sections, and you can see that we can turn off or on the plotting. So let's back to the main code. So we are going to define the two concrete sections for beams and columns, and in here we're going to define the elements of these 27 elements, and also in here we're going to apply the distributed load for all beam sections, and thermal loads just for elements 6, 7, 8 and 9. So these thermal loads going to be applied just the beams in story 1, and we're going to run the analyze as a load control. So I defined the info link for better understanding of each steps, and also we're going to output the displacement and base reactions of each nodes, and also strain and stress relations for concrete and also steel rebars. And in here we're going to run the each steps, and then outputting the temperature and displacement in X and Y directions. Middle node is node 18, which I told you. And then after running the analysis, we're going to plot the form shape of these structures with a scale, for example 10 times bigger, and then outputting reading the outputted data. You see in here. So in here we're going to read the outputted data, and then in here we're going to plot the result. So let's see the 2D steel frame thermal file. So in 2D steel frame thermal file, all process is the same, but the section of steel, for example in here steel frame section is different. So all parameters such as these parameters as a number of stories and bays, and also is the same, but in here we use the different properties for these steel frame structures for material properties, and also thermal and distributed load is the same, and number of steps is the same, geometry is the same. And in here we're going to in here let's see yes, in here we're going to define the beams sections as an I section, and also for columns we define the double I sections. As I told you and show you that for beams and columns we have different shapes. So we use this I section for definitions of the beam sections, and also this double I section for definition of the column sections. So let's see the open Python code of definition of this beam section and column sections. For definition of these two different sections, we define the Python code as a steel fiber thermal sections, and you can see that in these two functions you can change the properties with with your own data for definitions of these concrete sections, and so you can turn off or turn on the plotting. You see, guys, the most important things in here, for this thermal analysis, we must define the fiber thermal properties as a section. And see, guys, I defined the different sections, as I told you, for circular pipe sections, and also rectangular tube sections like box sections, and also rectangular sections. So you can change this section properties with your own defined section. So let's back to the OpenSees file. So all process is the same as concrete frame structures analysis. So we're going to define the elements and uniform distributed load, and also thermal load in these beams, and running the analysis and outputting the displacement and different base reactions, and also strain and stress relations of defined nodes. And then in each step we're going to output the temperature, displacement in x and y directions of this degree of freedom, not 18, but in here we're going to output the node 6 for better showing the lateral displacement of the story 1 of a beam's lateral displacement. So displacement, we're going to output the displacement in node 6 and 18, and also all process is the same, and we use this plot frame shape as a 500 to better plotting the form shape, and also trying to read all outputted data and then plotting the outputted data. So as I told you before, we have 5 different steel sections, so you can change it with your own parameters and then run it again. These codes are available in my GitHub. You can download it and change it with your own. My target is just educational purpose. It's free, and you can see the links of my GitHub in description below. And you see that after running the analysis, the undeformed and deformed shape of these steel frame structures with the form scale as a 500 is like this, and different result as a strain and stress relations of node 6 is going to be shown in here. This Python code useful for engineering and researchers interested in accessing the effect of thermal variations on concrete and steel frame structures. By simulating different temperature scenarios, we can evaluate the potential issues such as thermal expansions and stress relations with, for all section properties. Engineers can use such simulations to design fire-resistant structures and predict the failure mechanism. So, for the other analysis, we're going to have an optimization problem. So, in this video we developed 3 types of optimization problem with different algorithms. First of all, Newton-Raphson method. The second is genetic algorithm. And the third analysis is optimizations with decision tree regressions modeling. So first of all, we developed the Newton-Raphson method optimization problem. So our target is to see that these nodes as a node 6 lateral displacement must be less than or equal to the demand displacement. So we are going to define the formula. So supply comes from an analysis as a thermal analysis, and we're going to define the demand. So demand displacement. So in this analysis, demand displacement is 60 millimeters, and by these definitions as F, we're going to develop the Newton-Raphson method and finding the best optimum rebar diameter sections. So our target is find the best optimum rebar diameters which prevent the lateral displacement of this node to less than or equal to the demand displacement. So we're going to find the optimum rebar diameters of concrete sections of this column and beams sections. See guys, you see, after 11 iterations we get the solutions of optimum section rebar diameters as a 39 millimeters. So 11 iterations for this kind of analysis is very nice, and you see the time is very good for this analysis. So after 11 iterations we get the solutions of this optimal rebar diameters, and you see all process is the same, and then we're going to output the displacement and base reactions of shear moment and axial reactions, and also strain and stress relations for this optimum steel rebar diameters, and also the form shape of this node is like this with the form shape of 10. And you see this Newton-Raphson method is very efficient, and I recommend you guys to use this kind of, if you have a optimization problem of this complex structural analysis, use this Newton-Raphson method. So let's see the OpenSees file, and you see in this OpenSees file all process is the same for defining the analysis, and in here we define this Python code as a functions for because we want to call this function many times. Okay, so in here we are going to define the initial guess of rebar diameters, and by the finite difference derivative method we're going to calculate that this derivative of f, and you know this kind of derivative is very nice for running the very complex nonlinear problems, and also residual stress and initial iterations and maximum iterations and demand displacement. So in this example, as I told you, demand displacement of node 6 is 60 millimeters, and you can change it with your own data. And you see, at the first we're going to run this thermal analysis, and then outputting the displacement, and then define the supply. So supply minus demand equals to F. And in a second analysis, we're going to decrease the X as X a minimum, and then run it again for finding the F a minimum. And in the third analysis, we are going to increase the X and then run it this temperature or thermal analysis, and outputting the displacement, and then F maximum as a supply maximum minus demand. We're going to find the F minimum and F maximum, and then we are going to use this finite difference derivative of F, okay, for calculating of the derivative of F. And by these calculations, we are going to run this Newton-Raphson method, and in each step we are going to output the residual and section rebar diameters. And if it is converged, so the optimum section rebar diameter is going to be shown. As I told you, after 11 iterations we get the solutions. So this Newton-Raphson method, I recommend you guys to use it. It's very nice. And also plotting data is the same as last analysis. So let's see the genetic algorithm. So in genetic algorithm method, our target is the same as Newton-Raphson method. So we want to find the optimum concrete sections rebars, actually best optimum rebar diameters. And you see guys, all process is the same, and also this function is the same. And you see that in here we are going to define the genetic algorithm optimizer and define some codes for generating and running this genetic algorithm method. See guys, bounds for rebar diameters, minimum 6 millimeter until 60 millimeters. Population size is 30, and also mutation rate and crossover rate. So you can change it these two parameters to find better convergence. And you see we're going to calculate the time durations by this genetic algorithm. So let's see the result. So you see that our process of these definitions of this concrete frame structures as a thermal loading is the same, but if you want to find the best optimum rebar diameter of this beam and column sections with this genetic algorithm, it takes near 25 hours So it takes so much time, guys. As I told you before, for this kind of analysis, it's so good to run this Newton-Raphson method. So you see that after 153 generations and 25 hours, we get the solutions. But in Newton-Raphson method, it takes so much less time for running this kind of analysis, and all outputted result is the same as Newton-Raphson method. So let's see the decision tree regression modeling. So in decision tree regression modeling, you see that we're going to develop the 200 iterations to generate all this decision tree process, and then after these 200 iterations, the optimum rebar diameters is going to be calculated exactly like as genetic and Newton-Raphson method with these seconds, guys. So let's see the decision tree regression modeling for finding the best optimum rebar diameters. So all inputted data and functions is the same, but in here, yes, we're going to define the decision tree regression parameters. So expand as a minimum until maximum. Demand displacement is 60 millimeters, and also number of samples and tolerance is going to be defined in here. And then in decision tree optimizer, we're going to run this decision tree regression modeling, and you see, so we defined 200 samples. As I show you, by these 200 iterations, first of all, we're going to generate many data as a rebar diameters and maximum displacement of node 6 lateral displacement. And after these 200 iterations, we're going to find the optimum rebar diameters based on decision tree regression modeling. So you see that these functions parameters in each samples, we're going to output the displacement and then run it the train decision tree regressor and finding the properties, and then in here we're going to predict the displacement, and then outputting the best diameter, final residual temperature and displacement of each directions. And you see that after 85 minutes we get the optimum solutions of this decision tree regression optimization problem. And also you see that all the plotting frame and also outputted data is the same as genetic algorithm and Newton-Raphson method. And at the end, I also run the uncertainty analysis conditions of these two-dimensional concrete frame structures applied with the applied thermal loads. You see that. So let's see the first of all result, and then we back to the OpenSees file. So in uncertainty conditions, we're going to define each element and materials and also loads properties with using beta probability distribution functions and with different alpha and beta coefficients, and run it 6,000 times, and then outputting the data such as displacement in x and y direction, and also different base reactions of these concrete frame structures. So you see, guys, we are going to use the beta probability distribution functions with the different alpha and beta coefficients for definitions of these different section and material and structural properties. So for definitions of the height of each story, I used this probability distribution functions. These probability distribution functions, alpha equals to 2 and beta equals to 1. So we're going to define the minimum and maximum variables for this height of the story, and then alpha and beta coefficients. And also for width of the bay, you see that I use this probability distribution functions with definitions of the minimum and maximum, and alpha equals to 2 and beta equals to 1. And you see that, so yield strain of steel rebar, I use this probability distribution functions with alpha equals to 1 and beta equals to 2. So I'm looking for critical conditions. So I increase the elements length and decrease the elements strength. So in here you see that model of elasticity, I use this kind of probability distribution functions, and also ultimate steel strain, you see that, and for concrete properties, I use these probability distribution functions, and also peak strain of the concrete, I use this probability distribution function. So we must define the minimum and maximum, as I told you, and also alpha and beta coefficients for this beta distribution functions, and also ultimate stress of this concrete properties. And you see that temperature, I used alpha equals to 1 and beta equals to 1, so it has the uniform probability distribution functions, and also distributed load is a uniform probability distribution functions as alpha equals to 1 and beta equals to 1. So for this temperature, minimum is 500 until 800 degree of Celsius, and for this distributed load minus 003 until 0025 as a uniform distributed loads. And let's see the other, rectangular sections start from here until here with the minimum and maximum values with these probability distributions functions, and also height of the concrete sections is like this, and also define so we are in uncertainty conditions, so all the variables, our input variables, we must use this beta probability distribution functions with different alpha and beta. See the rebar diameters. Minimum is 22 until 25, and after running this 6,000 analysis iterations, so we get the different result for displacement of in x directions, in y directions, and also rotations of the node 6, and also base axial and base shear and base moment. You see the base moment, base shear of this result, and also base moment of this 6,000 iterations uncertainty conditions analysis. And then we're going to use data, these outputted data, to find the best predictions of temperature effect. You see that this 6,000 data for displacement and different temperature, it's going to use with this linear regression. So the R squared is not good for this analysis, for this linear regression. So we use the other method as a clusters. So we divide this all nodes to the 9 parts. So, and based on this cluster modeling, you see that R squared is very good. And you can see that the other outputted data in y directions, R squared is very bad. But we use this cluster method with good R squared. And you see that the base axial and displacement direction, displacement 6, R squared is 0.2, but the cluster method is 0.9. So it shows that this cluster method is very efficient for this kind of analysis, which we can't use the regression modeling. And you see that the displacement y and base shear, R squared is 0.3, but the R squared is 0.87. And you see that other outputted data such as base moment and rotations is R squared for this linear regression is that value, and then cluster method is this value. So it shows that we can use this method for better classifications of these data and then use it for our design purpose. So as I told you, we have different outputted data such as displacements in x and y direction, rotations, and base axial, and base shear and base moment. So we use the correlations heat map for better showing the relations between this outputted data. You see that, and I use the multiplier regression for this outputted data, and you see that for example this value, and this value and this value don't have a very good p-value, so we must omit some data and then run it this multiplier regression for better finding the linear relations between each parameters. And I also run the Markov chain matrix for finding the damage criteria for this analysis. So I define the different displacement, lateral displacement, for example, no damage level, minor damage level, and also moderate damage level and severe damage level. So with the different values, and with this Markov chain transactions matrix, we can find these damage levels with this matrix method. And you see that, for example, these positions, you see that the transaction percentage relations between failure and no damage is going to be shown in here, and also minor damage and also severe damage. This Markov chain is very nice for calculating the risk analysis, and I recommend you guys to use this kind of analysis for better predicting the failure behavior of this kind of structures for your modeling. And at the end, I did the reliability analysis, and you see that the blue bars is a capacity and base shear of these elements going to be shown in here. So it shows that the probability failure is 0.21, so 21%, and based on this reliability index is 0.96. This code, which I prepared for educational purpose, and you can download it in my GitHub channel. So let's see the OpenSees file as a Python code. So you see that in here we're going to develop the story height as a beta distribution functions from minimum and maximum with this alpha and beta, and number of simulations, which I told you, with 6,000 simulations for story bay, and also yield strain of steel rebar, and also ultimate steel strain, and also concrete comprehension strain, and also other parameters such as maximum thermal loads. We defined minimum until maximum with alpha equals to 1, beta equals to 1 as a temperature, with a 6,000 number of simulations, and also distributions functions from minimum until maximum. And see guys, and also rectangular sections for different properties of these concrete sections. And you see that we're going to use this beta distribution functions, and you see in each step we are going to use these random numbers and then running this thermal analysis, and then outputting the data such as displacement and base reactions, as I told you. And you see we're going to run 6,000 simulations, and after this step is going to be finished, then we're going to output the different result. So we're going to load all 6,000 text file, different nodes, base shear and base moment, and also base axial forces and displacement, and also strain and stress relations of this concrete bottom and top fibers. And also, as I told you, we're going to plot it with the linear regression and also cluster data with 9 divisions, and you see that the different data, we're going to use this linear regression and cluster method. And you see that in here we're going to plot the correlations matrix, and also I use the random forest data, so you can run it, and you can define this target displacement and then run it, and multiply regression and also reliability analysis. And you see that the Markov chain, and let's see the other. And also after Markov chain model, we are going to model the machine learning method. So the machine learning method with this number of simulations, it takes so much time, guys. So I didn't run it, but the codes are available, so you can change the model to the simple data and then run it with your own. So let's see the solar math and also Markov chain functions. So in solar math functions as a file, I defined many functions such as beta PDF, histogram, all functions which are needed for plotting the data. And you see that the LSTM method as a long short-term memory, algorithm method, reliability analysis, and multiple regressions model, a random forest model, and also plotting the time history outputted data, and also plot the different linear regressions. And you see that by changing the order, you can change the model to the polynomial modeling. And also we're going to use this cluster data, as I told you, with this algorithm for predicting and dividing the all outputted data to the divided sections. And you see that in here we are going to calculate the optimal cluster and also R squared for this kind of modeling with the cluster method. So that's all. These codes are available in my GitHub, and you can download it and change it with your own modeling. And if you have a comments or even have a question, you can email me or even comment in below, and then tell me now about this kind of modeling. These videos which I prepared for just educational purpose. God bless you guys. Bye.